Okay, hi everybody. This one's not bad. We got this rational function. Rational function, we call it that because it's a ratio of two polynomials. This is a polynomial and this is a polynomial. And all we have to do is divide them, so it's not so bad of a function. Now here, this is not a rational function, it's just a polynomial. So it's even easier. Okay. Anyway, compute the first three derivatives of each. Okay, so first of all, let me just remind myself that 1 over x is the same as x to the negative 1, so its derivative will be negative 1 over x squared. This is something you should just know. The derivative here will be, well, let's see, negative 2 times negative 1 over x to the third. The derivative of that will be negative 3 times negative 2 times negative 1 over x to the fourth, etc. So anyway, that was all just me making sure I can do an easier problem. Now let's do this one. 1 over 1 minus x. Derivative gives what? Then the chain rule, I have to go in here and take the derivative of that, and that pops out another minus sign, which means a minus times a minus is a plus. Let's take the derivative again. So here I'm going to get a minus 2 over, now this becomes over to the third, and then the chain rule gives me another minus sign, which turns this into a plus. Take the derivative yet again, I get a minus 3. A minus 3 is going to come up here and hit the 2. And then the chain rule brings another minus sign, which gives me a plus. Okay, and I'm supposed to evaluate them, so at x equals 0, well, the function just gives 1. This gives 1. When x is 0, I get a 2. When x is 0, I get 6. Okay, this is the function value at 0. The derivative value at 0. The second derivative value at 0. The third derivative value at 0. Okay, sort of like some curvy curve at a particular point. It has a line, and then maybe a conic, and then a cubic, and then eventually you get the whole curve if you go infinitely many. Anyway, let's do this one. Okay, instead of 1 over 1 minus x, I'm doing this. Okay, so the derivative gives the derivative again. And one more time. And evaluate at x equals 0, x equals 0, x equals 0. And there we go. Okay. So how do we form the power series? Well, if we know derivatives of our function and we can plug into our function already, then it's going to be this, just all the derivatives, and maybe we're going to have to divide by some factorials, which will be these sort of 3 times 2. So 6 is really a 3 factorial. And in general, we're going to have like f some derivative at the point a divided by n factorial x minus a to the n. Sum, n equals 0 to infinity, is a Taylor series expansion. This means the nth derivative evaluated at the point x equals a, because that is where we are centering our power series. Okay, so we're somewhere, instead of centering it at x equals 0, like we did here, we're not going to get a power series just in x, but a power series in x minus a. And so wherever we want, let's say we're interested here at the value x equals a. Well, near there, the function has some value. f0 of a is just evaluate the function at a. And then we're going to get to the first order, we're going to get some sort of a line with a slope given by f prime of a. F first derivative evaluated at a will give the slope of this line. And then f double prime evaluated at a divided by 2 factorial will give sort of what the tangent conic should be when we multiply by x minus a squared, and etc., etc., etc. We're going to get better and better approximations to the real function near the point A. Who knows what it's doing over here and here?